Hi, my name is Malte Ostendorff and I'm presenting to you our COLING 2020 paper, Aspect-Based Document Similarity for Research Papers. This is a joint work with Terry Ruas, Till Blume, Bela Gipp and Georg Rehm. With this paper, we present an alternative approach to document similarity. Document similarity is essential to many information retrieval applications like recommender systems. In content-based recommender systems, recommendations are generated based on a similarity measure between a seed and candidate documents. So the most similar documents are used as recommendations. But this notion of similarity has a shortcoming. Because whether two things are similar or not highly depends to what the similarity relates. Especially with long documents like research papers that tend to cover several aspects of a topic, two documents can be similar in many different ways. So instead of just measuring a single degree of similarity, you need to rather measure similarity with respect to the aspects that makes two documents alike. For example, research papers can be similar regarding their method or the findings. But today's document similarity measures are not really equipped to provide this kind of aspect-based similarity. And that's why we propose to solve this problem with the pairwise, multi-class, multi-label document classification task. Pairwise means that we have a document pair, let's say A and B, that are subject to our classification. The classification is multi-class because we have multiple aspects and that A and B can be similar. And it is multi-label because the pair can be similar in one or more aspects at the same time. And we consider this a supervised learning problem. So we have positive and negative training samples of document A, B, and the corresponding labels. And because of that, we need training data. So in the context of research papers, one common approach is to use citations as training signals, so also as training data. The intuition is that when two papers are connected through a citation, you can assume that the two papers are similar. For the classification task, this would correspond to a binary classification. So the question would be, does a citation exist? Yes or no, similar or dissimilar. But we want to go beyond a simple similar or dissimilar classification. And therefore, we do not only ask whether a citation exists or not, but instead in which section the citation is located, and use the corresponding section title as label for our multi-class, multi-label classification. So for example, when the seed paper cites the target paper in the introduction section, introduction would be the label for the pair of seed and target paper. Following this approach, we conduct experiments on two research paper corpora, namely that is the ACL Anthology reference corpus and the COVID-19 open research dataset, or short CORD-19. The extracted labels can be seen in those two tables. And what you already see is that one problem is that the class distribution is unbalanced. And this is, of course, because the inconsistent use of section titles. So there is a large variety of section titles in our corpora. And to make the dataset a little more balanced, we decrease the label space. So we only take the 9 most popular section titles from the two corpora and one additional class, that is the other class, for the remaining section titles. And this is, of course, some kind of simplification and leads to ambiguous label classes that are not that easy to distinguish. For example, you see the experiment class or the method class, where you could expect that those sections or labels overlap. But this is not crucial because we have the purpose to get a more fine-grained similarity assessment. So you need to see it rather in contrast to the binary similarity labels. And to illustrate this, let's look at some examples from the ACL Anthology corpus. One is here the seed document is the query segmentation based on eigenspace similarity. And that cites the target paper, unsupervised query segmentations using generative language models and Wikipedia. And the target paper is cited in the introduction and experiment section. And that's why we have the corresponding labels here. The second example, there the citation occurs in a section that is not part of our top 9 titles. So that's why we have the other label here. The third example is one example for a negative sample. So it's an unrelated pair of papers, which we randomly sample and which don't share any citations, co-citations, or co-authors. And we generate these negative samples, so pairs with this none label, and the same amount as we have positive samples to improve the training. Based on these 2 data sets, we then evaluate 7 systems. As baseline, we have a LSTM with fast text word vectors that were pre-trained on the datasets. And we compared baseline to transformer models. And as transformer models, we have BERT, the original version, and then COVID variation trained on the CORD-19 dataset, SciBERT trained on general scientific literature from different domains, and also RoBERTa, XLNet, and ELECTRA. All the transformer models are used in a sequence pair classification setup. So we have the title and the abstract of the seed and the target document, both separated with this SEP token. For implementational details, please look at our paper and also on GitHub, where we have all our code and data and models available. Okay, let's look at the results. So we evaluated the systems in a 4-fold cross-validation. The total dataset size for ACL was approximately 70,000. For CORD-19, it was around 100,000. We report F1 score, precision, and recall. Also for the F1 score, the standard deviation, and both as macro average and micro average. For the ACL dataset, SciBERT achieves the best results. We have in particular for the macro average a large margin compared to the other methods. Generally, the difference between macro and micro is caused by the unbalanced class distribution that we saw before. For the CORD-19 dataset, we see a similar outcome. Again, SciBERT achieves the best results. And the reason for this outcome, we see it in the in-domain pre-training of SciBERT. So SciBERT was pre-trained on a large variety of scientific literature that included both biomedical for the CORD-19 dataset, but also computer linguistics papers similar to the ACL Anthology dataset. Generally speaking, the BERT variations, so the original BERT, SciBERT, COVID-BERT, perform better compared to the LSTM baseline and the other transformer-based models. We attribute this to the next sentence, a prediction objective that is used in the pre-training of the BERT variations, but not with RoBERTa, XLNet, or ELECTRA. And the next sentence, prediction task, is very similar to the pairwise document classification that we are doing. Aside from the overall results, we also investigated the performance for different label classes. So as a reminder, each class represents a different section in which a paper is cited. So the section indicates in what aspects 2 papers are similar. But the aspects can be also ambiguous, making the label classification a hard task. And in the results here, we see that the non-label, the non-class, so negative samples, yield the highest scores by a large margin for both datasets. The other class, so rather positive labels, show the second highest F1 score. And the other class does not really represent a specific aspect. only that a citation exists, so it can be interpreted as a opposite of the none class. The remaining positive labels yield lower scores, but also have lower number of samples. But still, lower numbers of samples does not necessarily correlate with a low accuracy. For example, in ACL, the label related work with around 3,000 samples yields higher scores when compared to introduction here with around 4,000 samples. But also for CORD-19, the label background has an F1 score of around 60, despite having only 113 samples in the test sets. So all in all, the discrepancy in the number of samples and the difficulty in uncovering latent information from the aspects contribute to the decrease in some labels' accuracy. For better understanding, we also manually analyze examples. Here we see the same examples from earlier, but also with the predictions from SciBERT. The first example, we see that all labels, the introduction experiment, are correctly predicted. Same for the example 3, the non-labels also correctly predicted. More interesting here are the wrong predictions, namely here the second example, where the target paper is the summary of a semi-oral shared task, and the seed is a submission to this particular task. So even though the prediction of introduction is wrong, given our ground truth data where we have other as labels, we would argue that indeed it would make sense to cite this shared task paper in the introduction of the submission. So the prediction is not too bad either. Aside from those examples, we also list additional examples in our paper. And from all those examples, we find that the manual evaluation confirms our quantitative results. So the model is indeed able to predict the aspect-based similarity with promising accuracy. Okay, so what kind of conclusions can we draw from our experiments? We applied pairwise, multi-class, multi-label document classification on research papers to compute their aspect-based similarity. We use citations and their section titles as aspect labels. Our goal was to test this approach as an alternative to the standard document similarity that only distinguishes between similar and dissimilar documents. Overall, we found that SciBERT performed best in our experiments. And despite this challenging task, SciBERT predicted the aspect-based document similarity with F1 scores up to 83. Moreover, our manual evaluation suggests that when relating the similarity to aspects, it is easier to understand what two research papers have in common. And particularly this motivates future work. One current issue is, of course, the dataset. Using section titles as labels and citations has its shortcomings. So we saw that titles are inconsistently used. Also, citations are used with different motivations. So that means that the section does not necessarily indicate the aspect. So that's why we're currently focused on improving the dataset, but also working on defining a fixed set of aspects for all scientific domains. In addition to that, we are integrating this approach into a recommender system to really evaluate this with actual users. Okay, thank you very much for your attention, and please feel free to reproduce our work. All our code, data, models are available on GitHub, and we even have a demo on Google Colab where you can try our pre-trained models with your own papers. Thank you very much.